Good morning all. So we'll move to the third part of the sixth module. I hope you have already understood what the theory portion of compaction is. In the earlier two videos, I beg your pardon, we were discussing about what compaction is, how it is different from consolidation. Then we had discussed a laboratory test to find the maximum dry density and the optimum moisture content. Then we moved on to the choice of the test. Then we discussed what the compaction curve is, and based on which how to determine the MDD, maximum dry density, and OMC, optimum moisture content, etc. Then we had discussed a term called zero air voids line. Then we had moved to the quality controlling field, where we use a Proctor needle to determine the moisture content. Now, based on whatever little we have covered in the theory session, we will try to attempt a few problems based on the compaction test. Now here comes the first problem. In a lab compaction test on a soil with specific gravity 2.68, a maximum dry density was found to be 1.82 gram per cc at a water content of 17%. You're asked to find the degree of saturation and the percentage air voids. So fundamentally you are given with rho d max, right? Maximum dry density. It's given as 1.82 gram per cc. Now we know that rho d or dry density is g by 1 plus e into rho w, where g is the specific gravity, which is already given. E is the voids ratio, which we don't know. Rho w is the density of the water, right? Which we usually take as 1 gram per cc. Now we had discussed in the theory portion that the E, voids ratio that you see in the denominator, can be replaced by Wg by S, right? Quite like this, where W is the water content, G is the specific gravity of the solid soils, S is the degree of saturation. Now, once we have reformatted to this formula, G by 1 plus Wg by S into rho W, we know a few terms which are already given in the question, right? You know specific gravity G, you know water content, and you know rho W. So water content is 0.17, which is nothing but 17% given in the question. Specific gravity is already given 2.68, and rho W, we all know the value of it as 1 gram per cc, right? So once you substitute that, the only unknown in that equation turns out to be S, which is the degree of saturation. So once you solve that equation, you get S as around 0.94, or you can rewrite it as 94%. Now, the second part of the question, you're asked to find the percentage air voids. Now, percentage air voids is nothing but Na, right? So you have an equation connecting Na and rho d, which we have already discussed in the theory portion. Rho d equal to 1 minus Na by 1 plus Wg into G into rho W, right? Where G is the specific gravity, W the same thing, water content, rho W is the density of water, rho d is the dry density. In this equation, the values of rho d is known, the value of G, specific gravity, is known, the value of water content W is known, and the value of rho W, density of water, is known. So the only unknown value turns out to be Na, which when solved gives you a value of around 1%, right? Now this is quite a simple question that you can expect for, let's say, around 5 marks, not more than that. Just an introductory question. I hope you have understood the question, the soul of the question, and the solution. Now here you have a second question. You have a lab compaction test on a soil which gave the following results. You're asked to find the OMC and the MDD, and you're also asked to plot the zero air voids line and 5% air voids line for a specific gravity of 2.72. So the question has got 5 sets of reading for bulk density versus moisture content. Bulk density is given in gram per cc and moisture content is given in percentage, right? You're asked to find OMC and MDD. This is quite a representative question based on the laboratory test. In the laboratory test, this is a format in which you get the output. You have the bulk density and you have the water content, right? So once you know the bulk density and the water content, you need to find the dry density using the formula rho d equal to rho by 1 plus W, right? For instance, if I have 2.06 as a bulk density and the water content corresponding to it being 12.85, I can get the dry density corresponding to that bulk density, right? 2.06 by 1 plus 12.85 is converted to a decimal format as 0.1285. So the dry density turns out to be 1.82, right, for this set of reading. Likewise, you can take the next reading, 2.13 the bulk density, 14.28 the water content. You will get another value for dry density, right? Turns out to be 1.85. Likewise, you have to find out the dry density for each of the values of bulk density given, which when solved gives a set of readings as shown here, 1.82, 1.85 up to 1.81. Now for us to find out the OMC and MDT, we have to have a plot, the compaction curve, which has water content on the x-axis and rho d, dry density, on the y-axis, right? So you have dry density here, you have water content here. You can fundamentally draw a plot which is a compaction curve based on these set of values: water content, dry density. You have water content here, you have dry density here, right? So you'll get a plot quite something similar to this, a bell curved plot, the peak point of which corresponds to a value of maximum dry density and optimum moisture content, like this. So in the exam, you'll be given with the graph sheet. In the graph sheet, once you draw this plot, you can draw a straight line and try to get the value corresponding to MDT and OMC. So in this particular question, when solved using an Excel sheet, the value I get is around 14.9% for OMC and 1.87 gram per cc for dry density. Of course, it might differ for a few decimal points if you are not using the Excel, and if you try to sort for a graph sheet, again, it depends on the personal errors that you make in the exam hall, etc. But nonetheless, the value should fall in a range, let's say, from 14.7 to 15.1, etc., etc. So the first part of the question is already covered, OMC and MDT. Now we'll move to the second portion, wherein you're asked to find the points for 0 Edwards line and to plot that, right? So you have water content here. You've already drawn the graph of a compaction curve. You know the equation rho d equal to 1 minus Na by 1 plus Wg into G rho W, right? And for 0 Edwards line, you know that Na is equal to 0, right? Percentage air voice is equal to 0. Now if you can substitute that and get these values, right? So based on this equation, once you substitute Na equal to 0, you will get a set of values corresponding to the water content, right? So this line, the points represent the 0 Edwards line. Now the third part of the question is to find or to draw the plot for 5% airboats line, right? Which means you have Na equal to 5% or 0.05, right? So quite similar to this procedure, you substitute Na is equal to 0.05 in this equation. You substitute the value of water content 14%, and you will get some value here. Likewise, you continue the process for 5 different values of water content, and you'll get something like this, right? So fundamentally, you've got the Y readings for 0 Edwards line and Na equal to 5%, and the X reading is the same thing, the water content that you've already used in the previous plot. Now once you know the X and the Y values, we can draw a line. 0 Edwards line is there, and then you can have 5% Na value line, right? Now we'll move to an application numerical problem apart from the theory portion. Here goes a question. As per the compaction specification, a highway fill has to be compacted to 95% of standard product compaction test density A borough area near the project site has a dry density of 1.65 gram per cc at 100% compaction and natural voids ratio of 0.61. The specific gravity G is 2.65. We are asked to compute the volume of the borough material needed to construct a highway fill, which is 5 meter in height, 1 kilometer in length with side slope 1 vertical is to 1.5 horizontal. The top width of the fill is given as 8 meters. Now, the story is quite simple. You are at the site, you are asked to construct an embankment with the following dimensions: 1 kilometer or 1000 meter in length, 5 meter in height, 8 meters the top width, and the slope is given as 1.5 horizontal is to 1 vertical, right? It looks quite similar to this. You're asked to construct such an embankment using a soil that you take from a borough pit, which means you're trying to excavate the soil from somewhere else, and you transport the excavated soil and you dump the soil on to this site, and you try to make an embankment like this, right? Now, the dimensions of the embankment is given here: 8, 5, 1000, etc. And the borough pit is somewhere else, right? The borough pit has a dry density of 1.65 gram per cc, and the voids ratio, which I've represented as EB, is 0.61. So essentially, you are trying to dig a hole from the borough pit. You take the soil, which has this value of dry density and voids ratio, transport the soil to the site, and you fill the site to make an embankment like this. Now, the property of the embankment soil is different from the property of the borough pit. The volume of the embankment soil, the voids ratio, the voids ratio of the embankment soil is different from the voids ratio of the borough pit, right? So there lies the key in the solved solution of a numerical problem. Now, you know the top width has 8 meters, and you know the slope is 1.5:1, from which you can actually calculate the base width, right? So if you know 8 meter and if you know 1.5:1, you can calculate the base width as 23 meters, right? Now, once you know 23 meters here and 8 meters here and 1 kilometer here, you can estimate the volume of soil that is to be filled in this embankment, right? So this is essentially a trapezium in cross section. You take the area of the trapezium, multiply it by 1000 meters, what you get is the volume, right? So you can calculate the volume of the fill, which I've represented as VF, to be around 77500 meter cube, right? So based on the dimension, you have calculated the final volume of the soil which is inside this embankment once the construction is completed. Now, the question is different. The question is to compute the volume of the borough material needed to construct this fill, right? Which means the volume that you take from this. Alright, now we have calculated the volume of fill or the embankment to be 77,500 meter cube. Now, in the question it's given that the borough area has 100% and the fill or the embankment has 95% of the standard Proctor compaction test density, which means the borough area, if it has 100%, the fill will have 5% lesser density, right? Which is already given in the question, from which we can estimate the dry density of the highway fill. The dry density of the borough pit is given as 1.65 gram per cc here, and we know the fill will have 95% of it. So the dry density of the fill is 0.95 into 1.65, which is 1.57 gram per cc. So now we have the volume of the fill in the embankment and the dry density of it, right? Now we know one more thing, the specific gravity of the soil. Even if it's a fill or the borrow pit, the specific gravity remains the same, 2.65, because it's a property of a material, right? Now based on this, you know an equation connecting rho d and rho w, which is this: rho d equal to g by 1 plus e into rho w. I have written E as EF because it is the void ratio of the fill. We are talking about the void ratio of the fill, the dry density of the fill, and the specific gravity of the soil there. From this equation, once you know G 2.65, rho D 1.57, and rho W 1, we can calculate EF, which is nothing but the voids ratio of the soil once filled in the embankment, right? So EF turns out to be 0.69. In short, the soil which was earlier in the borrow pit had a dry density of 1.65 gram per cc with a void ratio of 0.61, and it got transported to the site where you are trying to construct an embankment of volume 77,500 with a void ratio of 0.69 and a dry density of 1.57, right? So the borrow pit had a denser packing, and the fill of the embankment now has a looser packing. Now, based on three-phase system diagram, in the first module we had said that when the volume of the soil is taken as 1 or unity, the voids ratio E is equal to the volume of voids. So when this volume is equal to 1, this volume is equal to E, so the entire volume can rather be represented as 1 plus E. You can flip back your notebooks and see these equations written there, 1 plus E. While we tried to derive a few equations, we had used this 1 plus E is equal to total volume concept, based on which I can write a relation for volume of borrow pit soil and volume of fill soil. VB by VF, volume of borrow pit soil by volume of fill, is equal to 1 plus EB by 1 plus EF, or the ratio of the volumes is equal to the ratio of 1 plus E terms, where EB is a void ratio of the borrow pit, EF is a void ratio of the soil in the fill. Now EB is known to us, EF we have calculated, VF we know, right? So EB is 0.61, EF we have calculated it to be around 0.69, and VF is a soil volume in demand for the fill, and the only unknown turns out to be VB, right? So the volume of the soil required from the borrow area or the borrow pit, VB, is equal to 1 plus EB by 1 plus EF into VF. Substitute these values and you get the volume required to be taken from the borrow pit. The story in a nutshell is quite simple. When 73,832 meter cubes of soil is taken from the borrow pit, it goes to the embankment and can be filled for 77,500 meter cube, because here in the borrow pit it was denser, and while transporting it got looser, and in the loose state it can occupy a higher volume. That is the essence.